Okay, we'll get started. We'll begin. So let's talk about our midterm exam, and that will be 1 week from today. I know it's like we just started this class, but yeah, next week is week 3, and so that will be like our halfway point in the course. So 1 week from today will be week 3 Thursday, and you'll have your midterm exam. And so I've posted in the modules this document that says midterm topics. Okay, and so this will cover pretty much stuff through. I mean, so most of it will be things that we've already seen, and then the last will be numeric gradient calculation for the neural network, which we'll cover in today's lecture, and then I guess Tuesday's lecture as well. But anyway, let's talk about each of these things. Okay, so our first is just calculating gradients in vector notation, and so I'm going to give you a function in vector notation, and you will have to find the gradient of that function with respect to a vector. So in the notes, you have seen like the ordinary least squares loss function in vector form, and you can kind of follow the process in which I've taken the gradient. Okay, you can, if you look at the textbook, there's also examples of them working through calculating the gradient in matrix notation. An important thing here is, as you work, make sure that the dimensions align. Okay, that can be used as a guide as far as, am I doing this step correctly? So if you write the dimensions of either your matrices or your vectors underneath each of the elements, you can just kind of ask yourself, like, if I have this thing and I'm trying to add this thing, you got like 2 matrices and you're trying to add them together, they have to be the same dimensions, right? Like if you have something that's like a 2 by 2 matrix and you're trying to add, I don't know, a scalar, that's not going to work. You probably have to multiply it by the identity matrix to make sure that it's in matrix form and these things can add. Or if you have some vector transpose another vector, make sure that when you take the gradient with respect to the thing, it's in the proper dimensions. So that's a guiding principle there for figuring out gradients in vector and matrix notation. We'll also have an example of, or a problem where you will have to do gradient descent manually. So I'm going to provide a 2-dimensional function. I'll provide you some arbitrary starting location, and I will also provide a learning rate, and you will do 2 iterations. You'll calculate where would gradient descent take you for time t plus 1, or time equal to t at 1 or t2. And so you have examples of this in on Tuesday's lecture, where basically we started here and then we took a step down the gradient. Okay, and so you can see kind of like manually how did I do this, and you would do this on the exam. Okay, so that's just to kind of make sure you understand how gradient descent works. You'll have some problems where you figure out your regularized loss, and so here I will provide like a tiny little data set. Okay, and I'll provide the line of fit for ordinary least squares regression, potential line of fit, and you'll figure out your OLS loss, just kind of your sum of squared residuals or your mean squared residuals. And then you'll also figure out your lasso loss, and you'll figure out your ridge loss. I'll provide the lambda values for those things, but basically add the absolute values in there, add the sum of the squares of the coefficients in there. This should be a pretty easy problem. Okay, I'll have a problem where you do some cross-validation manually. And again, this one, I'm going to provide a tiny little data set. And I will tell you, this is what I will fit, like if I have a small data set, I will remove one of the points and I will provide, this is what the fitted line is on the remaining points, okay? And I'll do that for each of these things, and you'll perform leave one out cross-validation. So, I'll have like, this is the leave one out when you remove, say, the first data point. This is the fitted line on the remaining data points, okay? And then so leave one out cross-validation will basically be, all right, let's plug in the point that was left out, see what value it predicts. Let me compare that to the actual value, and you'll get one of the values, and you'll have to do that for all of the points in your data set, okay? And so you'll have to, so each of the models I provide will have n different fit lines, and then and you'll find the mean cross-validation error for these the two competing models, okay? And you kind of have an example of, I guess, coding up manual leave one out cross-validation in your homework exercise, okay? But make sure you also understand, like, if somebody said do this by hand and with a calculator, like, you can at least do the process as well, okay? So yes, definitely you'll need a calculator, okay? We'll have, I'll introduce neural networks today, and then I'm going to ask you to calculate the gradient manually, okay, doing a numeric gradient calculation. And so numeric gradient is a matter of kind of plugging in, adding a small h, like a 0.01 or 0.1 or whatever, to one of your terms, okay, and seeing what effect it has on the loss function, right? So you allow it to kind of, you say, if I change the weight of this by 0.1, how is that going to affect the output, okay? And then you say, okay, this is how much the loss function changed, and that was based on a small change of 0.1, and therefore my estimate, at least for this component, is this. And if you have multiple elements in your matrix, which you will, you'll follow that same process through, okay? So it's you have an example of numeric gradient calculation right here. Okay, so here's an example of calculating the numeric gradient on this slide, slide 50, I guess. But this is, it's not neural network, it's just a two-dimensional function, but the same idea of you have to do it one element at a time, okay? You don't want to do it for like all of the elements in your matrix, okay? And then I'll have a handful of conceptual questions, and that's that. Oh, you will be allowed to have one sheet of notes with writing on the front and back. So one ordinary letter-sized piece of paper, okay? Writing on the front and back. It can be typed, it can be handwritten. My only requirement is that you make it yourself. I don't want you to like make a good one and then photocopy it for someone else or something like that, okay? I will collect the note sheet with the exam. So like if you want to keep it for your own reference or something, take a picture of it yourself. But I'll collect the note sheet with the exams. So that's what we'll have. I'll also send out like a seating chart. It feels a little strange, but I'll get a layout of the room, and then I'll kind of have assigned seats. And hopefully, are any of the desks broken? Do you guys know of any desks that are broken or here? Hopefully there's no broken desks, or if there is one, we can make sure everybody has a fully functional and operational desk and seat. Yeah, if there are anything, like if any of the desks or chairs are broken, let me know, and I'll pass the message on to UCLA facilities. They're actually very good about repairing everything. It's just they don't know. They don't know when something is broken, and a lot of times nobody says anything, and so something will just go. unnoticed and broken for a while. Okay, obviously, once they find out, it takes them a little while to maybe order parts and get everything replaced, but they are pretty good about fixing up things in the facilities. Okay, any questions about the exam or anything like that? Feel okay? Okay, so that's 1 week from today. It'll be taken right here in class. And that's that. Okay. All right, let's take a look at today's lecture. And so I want to talk a little bit more about regularization and the bias variance trade-off. Again, the bias variance trade-off gives us a handy, kind of spectrum and perspective on the different types of models that we can fit, okay? And a lot of the models that we think about kind of are, exist somewhere on the spectrum, and then there are things within each model that are like hyperparameters that you can change, and when you change those hyperparameters, it will kind of, on the spectrum be either, more on the high bias, low variance side, or it will lower bias and increase variance. And usually the optimal solution is somewhere in the middle, okay? We really only know what the optimal solution is if we know what the true data generating process is, but we're hoping to kind of figure this out. Okay, so we've introduced regularization, and we said the regularized loss function, when we think about how it has modified the loss function, it now takes into part two components. One is the ordinary least squares loss function that says we want to minimize the sum of the squares residuals, and that's still a priority, but we also have this other thing that we have to think about, and it combines the loss function along with a complexity parameter. So we want to minimize the sum of squared errors, but at the same time, we don't want to minimize it by making our model overly complex. So we kind of factor in both of these things together into one function, okay? And then which of these goals, is the complexity thing more important, or is the minimizing the sum of squares? That is weighted by a gamma or a lambda term, okay? And so we have this, okay? So the lambda term, or the penalty for complexity here, okay? And so this is kind of the idea. We have the ordinary least squares loss function right here, which is our kind of our fancy L, and then we add some kind of thing for complexity, and we multiply it by lambda so that the two ideas can be combined together, okay? So, as far as some kind of objective function, okay, our objective functions, basically it has to be like one-dimensional because we want to minimize that. If we have to think about too many things, it gets hard. So we just kind of add them together. The way we do it for lasso is we add in the sum of the absolute values of the coefficients in our model. So we add, whatever the sum of the absolute values times lambda, and then if we're talking about ridge regression, we add the sum of the squares of the values in W, okay? And there's something called elastic net. This is implemented in a function called glmnet, and this takes a hybrid of lasso and ridge regression. And so now we have two parameters here. We have a lambda on the outside. The entire complexity is now this thing that has two parts to it, okay? And we multiply that by lambda, so it's still lambda times complexity. It's just that complexity now takes in both the L1 norm and the L2 norm, okay? And we have a factor alpha, and it's alpha times lambda 1, and it's 1 minus alpha times, alpha times kind of the norm 1 of the W vector, and it's 1 minus alpha basically times the ridge regression part. And so if alpha is equal to 1, okay, this is entirely just this part. This part zeroes away, okay, if alpha is equal to 1. So that reduces down to lasso, okay? And if alpha is equal to 0, okay, this part disappears, and it's entirely just the L2 norm, which will be ridge regression, okay? And so so this is kind of another dial, like, do you want it to look more like lasso? Do you want it to look more like ridge regression? Or do you want something in between? Okay, and that's what alpha does. And this is described in the package, whoops, GLMNet. Oh, looks like that link is broken. So this is kind of like a mixing parameter of how much of each of these things. And so I just kind of took this quote directly from the documentation. And so ridge regression shrinks the coefficients of correlated predictors towards each other, right? So we saw the coefficients kind of becoming similar in value. And then lasso will tend to pick one and discard the other. So lasso kind of starts to shrink all the coefficients until some of them become 0. And so the elastic net penalty mixes these two. If predictors are correlated in groups, and alpha of 0.5 tends to select the groups in or out together. This is kind of a higher level parameter. A user might pick a value up front, or they might experiment with a few different values. And so, you know, that's what you have. Okay, again, lasso tends to push coefficients down to 0, so it can be used as a form of variable selection by kind of shrinking the smaller coefficients. They get shrunk down to 0 first. Okay, so GLMNet is implemented in this library, GLMNet, and I'll show you a few examples. You know, I am a fan of a bigger package called Tidy Models, and I teach that in my other class, 101C, and Tidy Models does have an implementation of using GLMNet with Tidy Models, but here I didn't want to get into all of the nitty-gritty of introducing that entire package ecosystem, so I'm going to just show you using GLMNet directly. Okay, when you use GLMNet directly, it requires you to format your data into an X matrix of predictors and a Y vector or Y matrix of response values. Okay. And basically, you're going to say, I want to predict my Y values based on X. All right. The default is to have alpha equal to 1, which is going to perform lasso. But again, you can pick alpha 0 or alpha 0.5, some other value between 1 and 0, and it will perform elastic net. Okay. And so here we just say, hey, predict the Y values based on our X matrix. The result will be our fitted object. And so as an example, I'm going to make some artificial data. In our artificial data, we have a total of 4 variables, and X1 and X2 are highly correlated with a correlation of 0.8. X3 and X4 are correlated with a correlation of 0.8. You know, and X1 is independent of X3 and 4, and X2 is independent of X3 and 4, and so on and so forth. And the true relationship is that Y in the population depends only on X1 and X3. Okay, and so in my data generation, okay, I'm using random multivariate normal to generate correlated values between X1 and X2 and X3 and X4, and then I combine them together into an X matrix, but you can see the true values of Y depend only on the first column of X, so that's X with a square bracket comma 1, and it only depends on the third column of X. Okay, so we use that to determine what the true values of Y are, and then I'm adding just random noise. I'm just adding random noise to all of my values of true Y. Okay, so the observed Y is going to be kind of like the true Y relationship, just plus some random error. And the question is can we figure out the relationships, okay? So I'm gonna take my X matrix, my output's Y. We'll start off with lasso, we'll fit GLMNet, okay? And this is the result of fitting GLMNet. You get this big long table, and it says, okay, this is degrees of freedom. Degrees of freedom is basically how many predictors you have. And so 0 degrees of freedom means you're not using any predictors, you're just predicting the mean for everybody, okay? And you're not explaining any of the center column would be like your R-squared value, okay? And so our R-squared value is basically 0. If we're just predicting the mean for everybody, we're not explaining any of the variance, okay? DF1 is like you've got one predictor, and lambda is pretty high, so we have shrunk that predictor down quite a bit, so its performance is quite poor, okay? And we can see our DFs increase from 0 to 1 to 2, and says, okay, now you've got 2 predictors, and now we are, our lambda is this much, and we're able to explain like 81% of our variation, or 90% of our variation, or 93% of our variation. So our R-squared value kind of keeps ticking up as I'm shrinking my lambda values, okay? So these are, this is the explanation of these 3 columns. So the first column is the additional degrees of freedom spent in the model versus the empty model. So basically each additional degree of freedom is the number of variables or number of parameters used in the model. The middle column is like the R-squared. It's the sum of squares of the regression divided by the sum of squares total. So that's going to be your percentage of deviation explained. And then the last column is the lambda term used by GLMNet. And so when lambda is big, you're applying a big penalty to complexity. So that's going to cause your values, your coefficients to shrink a lot. When lambda is small, you're applying very little penalty. Okay? And basically when lambda is 0, you have no penalty, and your model coefficients would be equal to OLS. Okay? So if we so if I use lambda equal to 0, then the resulting model will be equivalent to doing ordinary least squares regression. Okay, and so my coefficient estimates will be this, and we will have 4 terms. Okay, my DF will be equal to 4 if I have lambda equal to 0. Okay, because here this is my OLS model, right? So I'm saying predict Y based on my X variables. I got 4 X variables, and so it fits all of them. Now, for OLS, we would probably do tests of significance to see if all 4 of our predictors are significant. And OLS detects that the predictor for X2, or the coefficient for X2 and X4, are not significantly different from 0. So it does figure that out, but it still gives you an estimate for all 4 coefficients, right? And that's what we would see if we go all the way to the bottom, where I have lambda equal to 0, but we don't see that there. Okay. So you can see these are just different values. Okay. For lambda, we can start off with lambda equal to 0, and as lambda increases, the amount of my basically my R-squared value, okay, the fit $sign dev ratio, okay, that's basically the deviation, the variance, the ratio of that is explained, decreases as my lambda increases. And basically, we want to, if you are using lasso, okay, the point of the lasso is to reduce, introduce a bit of bias to reduce the amount of variance in your predictions. But as we introduce bias, we are not able to explain as much variation as before, and so our R-squared value goes down. You see almost like a little bend here. Okay, this is the effect of right around here is when we go from having 2 predictors down to 1 predictor. Okay, that's what that little bend is. Okay, this this matrix shows basically the coefficient estimates for different values of lambda. Okay, so S0, this is the very first one where the lambda is maximized. We have a very big lambda, and all of our coefficients are 0. Okay, and we're basically not using any predictors. Okay, for this is like the second largest lambda. This is our coefficient, and then for the next lambda, this is our coefficient. We can see as the lambdas decrease, our W's, the weights are for our coefficients, grow. Okay, and this is what we have. The default is to have what we call a sparse matrix. And so a sparse matrix basically only populates only values that are non-zero, and it puts little dots for everything else that is 0. Now, this might feel a little bit strange because it's like, where did all these numbers go? So you can print it as a matrix, and it will just populate everything that's a dot with a 0, with an actual 0 value. Okay. And here we can kind of look at the end, and in the end we have these different coefficients, 3.016 and negative 1.78. And this applies still just a tiny bit of lambda, okay? And so our coefficient for variable 2 and our coefficient for variable 4 are still 0 here, okay? And, you know, in the OLS model, the true coefficients, not the true coefficients, the OLS coefficients are 3.04 and negative 1.84, and you can see in our thing they've been shrunk down. The absolute values have shrunk down, have been shrunken a little bit towards 0. Okay. The coefficients for x2 and x4 are like negative 0.01 and 0.05, and I guess they've been shrunk enough to go down to 0. And if you just, yeah, and these are the OLS coefficients here. Okay. Okay. And so if you want, you can kind of specify a particular value of lambda, and you can say, okay, what happens, what are my coefficients if I have s equal to 0.2? Or what are my coefficients if s is equal to 1, right? So with s equal to 0.2, my lambda is 2.83. I mean, not my lambda, my coefficient for variable 1 is 2.83 and negative 1.63. And you can see that if I increase my lambda, the penalty for complexity here, then it causes the coefficient estimates to shrink, right? The absolute values to shrink. So we go from 2.83 down to 2.03. We go from negative 1.63 down to negative 0.95. So they've been shrunk towards 0. And these are for different values of lambda. Okay. The intercept is not part of the penalty calculations. So even though I'm increasing my lambda here, the absolute values of the intercept is actually getting bigger, but that's not part of the penalty calculation. Penalty calculation is only calculated on the absolute values of the coefficients for each of the variables here. Okay. So you might wonder, like, okay, well, what value of lambda should I use? Okay. So the reason why we're doing regularization in the first place is to prevent overfitting. Okay, is to kind of prevent overfitting. We want to see how well, we want our model to generalize to new unseen data, and what we're trying to do is we're trying to avoid having a model that fits too many I guess variables. Okay, and again, the traditional method would be to learn linear regression. You would do these statistical tests, and you'd say, okay, this variable x2 is not significant. This variable x4 for the coefficient for x4 is not significant, and we would keep these. Okay, but Lasso, being kind of a machine learning thing, is we don't want to have to think hard and make these decisions ourselves. So we're just saying, okay, if I use if I modify my loss function in such a way that I just automatically apply some kind of penalty to the complexity, is that going to just pick a better model? And we can see that applying a penalty does shrink my coefficients. Does that improve the model? The way we're going to calculate that is by using cross-validation. And so there is already a built-in function for cross-validation with glmnet, okay? And so we run this function called cv.glmnet, okay? And this says do 5-fold cross-validation. So this is automatically going to kind of split our data into these different chunks, you know, estimate these things. And then here on the x-axis we have different values of lambda, okay? And it says log of lambda, but basically on the right we have lambda equal to 0, which is no penalty, okay? And then lambda, and then over here we have, you know, I'm sorry, wait, log, why is my, okay, and then a negative value, so I have a smaller lambda. And so here we get an estimate for the amount of error that we have, okay? And so we can see the estimated values are in red, and so as over here, it kind of looks asymptotic in that, like, the amount of improvement we're getting doesn't change, isn't drastically improving or anything like that, okay? Because of cross-validation, sometimes the amount of error we calculate is bigger or smaller, and so we do get error bars on our cross-validation that just says this is kind of, we get different size things. Okay, oh, yeah, sorry. This is log lambda over here. This is like having like your lambda is so big that you have basically like no predictors, right? And then over here, I don't have the 0 over here, but all the way on the left-hand side would be something similar to ordinary least squares regression, okay? And the recommendation, so this vertical line over here is the minimum amount of error that we have. And I don't know if I can zoom in any further, but you were able to kind of see this location right there is the minimum amount, okay? They all look kind of the same, but these ones are technically just a touch higher than that one. So this is the minimum amount, okay? And then this dotted line over here on the right-hand side, this says the error bars around this one means this is not significantly different from this one, okay? So the rule of thumb is pick the largest value of lambda such that the amount of error that you have, because if you pick too big of a lambda, like you're shrinking your coefficients too much, and you end up getting really bad performance all the way on the right, okay? But in general, we want to try to pick a bigger value of lambda, but we're going to pick a value of lambda that is not significantly different from the minimum value of mean squared error. And so this value of lambda produces the minimum mean squared error. This value of lambda is bigger, but it's not significantly different from this, the amount of error that we have here, okay? So this is, I think, what we call the one standard error lambda. So yeah, you can ask, what is the value of lambda that minimizes the mean squared error in cross-validation? And it's this one, okay? And then you can also say, what is the largest value of lambda where the amount of error in that thing is, within one standard error here, okay? So that's the lambda.1SE, right? And so this is kind of like, if you don't have strong opinions, this is the one that we would recommend, okay? And so you can see this one, it's a larger value of lambda, 0.268 versus 0.05. And we can see our coefficients are indeed a little bit different. They are smaller, but the amount of error we're getting on this is not significantly different from the other one, okay, when we do cross-validation. Okay, so lambda min is the value of lambda that produces the smallest cross-validation MSE, but there is standard error, and so the lambda 1 SE is a larger value of lambda that still produces a fairly small cross-validation error, and it's within one standard error at the minimum. Okay. So the reason why we do this regularization, again, is to avoid overfitting, and we're willing to have biased estimators so that we can reduce the amount of variance in our estimates, okay? So OLS produces the best linear unbiased estimators, and best here means they have the lowest amount of variance among all other possible unbiased estimators, okay? But an issue is that if certain variables are highly correlated, the coefficients of those variables do exhibit high variance, and depending on your random data set, you might get bad estimates, okay? So we're gonna reduce the variance of the fitted models even further at the expense of introducing bias. And so what we're gonna do here is that I'm gonna just show you, what are some of the coefficient estimates that we get if I just fit a whole bunch of different random models, okay? So having less variance in the coefficients is a desirable trait of the models, and it means that when you have a random data set, the model estimates that you have are going to be, are less likely to be swayed by any of the kind of noise that you're going to get whenever you have random data, okay? And, in contrast, imagine fitting a model and based on one random data set, and then somebody else gets a different random data set, and you have very different coefficient estimates, okay? Now you're not going to be super confident about your current set of coefficient estimates, okay? On the other hand, if your values don't change very much, then you can feel pretty good, okay? So here what we're going to do is we're going to do kind of this simulation study, and what I'm going to do is I'm going to simulate some data, and again, there's correlation between x1 and x2, and there's correlation between x3 and x4, but the true values of y depend only on x1 and only on x3, okay? But we're going to add some random noise, okay? And so when I add random noise, okay, then we're going to, after I add the random noise, I'm going to say, all right, what is my OLS estimate? What's my lasso estimate? What's my ridge regression estimate? Okay, and I'm going to kind of just, so I take random values, we add noise, we're going to get OLS coefficient estimates, we're going to get lasso estimates, we're going to get ridge regression. So these are done by doing cv.glmnet, okay? And we have these different things, and we're going to pick the coefficients based on the ones that minimize the cross-validation error for the lambda.1 SE, okay? Okay, so what is this showing us, okay? So this, in the true model, the coefficient for x1 is 3, okay? That's the true relationship between the first x variable x1 and y, the true in that thing. And so we can see in OLS, it is unbiased, and so our coefficient estimates are centered around 3, okay? And but sometimes, because of random noise, sometimes we estimate something as high as 3.5. Sometimes we estimate things as small as 2.5 as far as this coefficient goes, okay? Lasso introduces bias, and so it's centered probably around 2.7, 2.65. And there's also variance. Sometimes it's higher, sometimes it's lower. So sometimes as high as 3.0, sometimes as low as 2.4, maybe even 2.3. This, I guess we have one observation down at 2.2. Okay. Ridge regression, again, also biased. It's centered maybe around 2.2, 2.3, somewhere around here. The amount of kind of spread here is I would say, a bit smaller. Okay, the highest we ever get is around 2.7, 2.8. The lowest we get is around 1.8. Okay, so I would argue a little bit less spread here. I guess this is similar. Like along the x-axis, we have kind of a range of 1.0, a range of around 1.0 on the x-axis, and here we have a range, I would say, bigger than 1.0 for OLS. So that's what we have for the coefficient for x1. Okay. If and this is just a little bit. So the mean for the model coefficient is 2.9 for OLS, and the variance is 0.06. If we look at LASSO, the mean is 2.7, but we have less variance, 0.03. Okay. For ridge regression, the mean is 2.26, and we also have less variance of around 0.04. So we do have less variance, but our means are off, right? The mean coefficient is off. This is what happens for our estimates for the x2, the x2 coefficient. So in the true model, the true relationship between x and y is that there's no relationship between x2 and y. Okay, so when we simulate the actual values of y, the true model has no relationship, and so it should be centered around 0, and that's what we see in OLS. However, because of random noise, sometimes OLS thinks there's a relationship when there's not, and so sometimes your coefficient for x2 is as high as 0.5, sometimes it's as low as, I don't know, negative 0.9 or something like that. Okay. Meanwhile, for LASSO, in almost all of our circumstances, it's estimating 0 for the x2 coefficient, okay? Which I would say is a good thing, okay? x2, so that's what it has. For ridge, again, it's biased, and ridge regression tends to push our coefficient estimates towards each other. So because x1 and x2 are correlated, the effect is that x1 gets shrunken down from its true value from around 3 down to around 2.2-ish, okay? And then the x2 there's no real relationship, but it gets pushed up from the true relationship is 0 to something around 0.5, okay? And by having x1 and x2 together in there, even though the true relationship only depends on x1 and doesn't really depend on x2, ridge tends to kind of push these correlated things together, and then kind of like when you add them up together, you end up getting like a reasonable, I guess, estimate, okay? So like the real relationship only depends on, I don't know, the number of bedrooms in the house, okay? But ridge regression says, oh, you know what, let's also take a look at the number of bathrooms, and we're gonna just kind of scale down the coefficient. You can kind of see like we've shrunk the coefficient for x1, but like we've inflated the coefficient for x2. So in combination, it gets, I mean, not a great estimates, but that's what we have there, okay? So that's what we have for x2. LASSO kind of correctly zeroes them out. So the mean of OLS is unbiased, okay? And it should be right around 0. And we also, but we do have a bit of variance, 0.087, okay? And again, when you have a random data set, you don't know if you're getting the one that's correct, close to 0, or the one that's high or low, okay? With LASSO, our mean is just kind of an artifact of our thing, is, I would say, is still pretty close to 0, but the amount of variance is a lot smaller. It went from 0.087 to 0.0087, okay? Ridge regression is biased, okay, but also less variance too. Okay, so we're introducing bias, getting rid of variance. Okay, and so you can see kind of how the effect it has on these things, and you would see very similar plots for variables x3 and x4 as well. Okay. Is that okay? The meaning of these these plots and what we're trying to show here. Okay, so a little bit more on the bias variance trade-off. Again, the total expected prediction area error is bias squared plus variance mathematically plus kind of the irreducible error in the whole thing. Okay, this is the sigma and the standard deviation of the noise in the generating data, or the variance of the noise in the generating data process. Okay, and here just to kind of illustrate this, I'm going to use low-S regression. We haven't covered this, but basically low-S is a non-parametric method that just kind of says, hey, try to fit a smoothing, like a smooth curve. It's similar to like having a rolling average. So like you can just kind of imagine having like this rolling window, and you're calculating like the mean or the rolling average. And low-S is basically, you have a window of points and you're doing weighted least squares regression, locally weighted, I don't remember, locally weighted least squares regression, basically on this rolling window. So it's like, if your data set spans this much, you just kind of first look at this thing and you just say, if I had to fit a linear regression line on this data, how would I do it, right? And then if I move my window over here, if I had to fit a linear regression line on this window of data, what would it look like? And you just kind of roll this window along, fitting these different things, and then you just kind of connect all of the things to kind of a smoothish curve. Now, one of the things that you can control is basically how wide of a window you want. All right, if you have a window that's super wide, basically it just becomes linear regression. Okay, if you have a window that's super narrow, now you can have this line that, like, it, I guess, is very flexible, or is very much influenced by just the few random points that are inside this window. Okay, so you can say how many values around X do you want to include in the regression. More values will result in a smoother fit. Fewer values will result in kind of a more jagged fit. And so basically, on one end, using a ton of values will have high bias, low variance. Using just a few values will have low bias but high variance, because it's going to be very much depend on this, right? So again, spectrum on the bias versus variance trade-off. And so just to kind of illustrate this, I'm going to say this is our true relationship. The true relationship is going to be just this very simple parabola, okay, part of I think it's a quadratic thing. It's just x squared, okay? It's just going to be the bottom of this parabola here, okay? But then what I'm going to do is I'm going to fit random points, generate random points around the true relationship, okay? So when I generate random points around the true relationship, this is what it looks like. And if I fit a model with basically a linear model here, this is the line, okay, that we fit. And the idea is, what if I do it again, okay? But this time I generate different random points, okay? So this is one, if you look at the dots themselves, this is one set of dots randomly scattered around the dotted line. And then here's another set of random dots scattered around the dotted line. And I said, okay, now fit a straight line to those random dots, okay? And then I'm gonna do this one more time. And so here, these are just different random dots, and I fit a straight line. So you can see the red curve remains exactly the same from one to the next. The dots are different, and the fitted line is also, the resulting fitted line is a little different. And so if I plot all three of those lines together, we have three similar but slightly different lines, okay? And so this is the idea of low variance, okay? So if I do this a bunch of times, each individual line is quite a bit different from the true relationship, okay? So we have, and if I averaged all three of these lines, that will still be quite a bit different from the true relationship. But how much do these lines differ from each other? Not very much. That's the low variance part. So high bias, low variance, okay? So here I'm gonna fit low S. Low S is the very kind of flexible part, okay? And so here I've got random data points, and I said fit a curvy line, and you can see it tries to get through the center of each of those data points very closely, okay? Here's another, I guess, another random set of data points, and the low S line tries to fit all of those dots very as much as possible, okay? And then here's one more, right? So if I plot all three of the fitted lines together, the lines vary a lot from one another, okay? So we have high variance, right? So if I say, hey, make a prediction at this location, sometimes the yellow will be like way down here, and the purple and blue are going to be way up here, okay? Make a prediction, you know, for this location, and you got, you know, three very distinct things. However, if you average all of these together, like overall, like the average of these 3 points, 3 locations overall is kind of close to the thing, right? So in the long run, you're going to have very little bias, okay? In the long run, the average value of these 3 predictors, like if you had all 3 of these things, and you would just say, okay, let's just calculate the average of all 3 predictions, okay? And you would get this, okay? And so you would have low bias, high variance, right? So that's what you have here. And so here I just did a whole bunch of these things just to kind of show you what happens in the long run if you do this like 1,000 times. You're going to see this this plot with all of this stuff here. But basically here I fit like I think this is like 1,000 or 100 linear regression lines, right? And so it's again you have a whole bunch of different kind of models fit, okay? And then this stripe of white dots here, this is the average. Like if I averaged all of the different lines together, this is the center of all of them, okay? And if I averaged all of them, this is the center. And so, you know, despite being like thousands of different things, they're all overall kind of similar to each other, especially in this like middle-ish region. They're all very kind of similar to each other. But how do the white dots compare to the true relationship, the curved relationship shown in this black line here? It's quite a bit off, okay? So when you average everything together, you got high bias that we've underfit, okay? And that's summarized and described on this this page, okay? This one is what happens when you do low S, okay? So with the low S, now you have all of these kind of spaghetti things, and it's, I guess this would be the uncooked spaghetti, and this is the cooked spaghetti, all right? And so these lines are super wavy, right? Super wavy, because based on the random data, sometimes like it's up here and then down here and then up here and down here, and so you have like all of these different kind of wild lines, and you don't know which line you are, okay? And so there's high variance from one model to another. It's like all over the place, okay? And if we picked one of the random lines and you didn't know which one it is, you don't know if like, is my value super high or super low? However, if you averaged, like if you had a whole bunch of these models and you averaged all of them, that's what these white dots are, okay? The white dots are actually very close to the true relationship. It's not quite like this white dot is above the black line and this white dot is below the black line, but overall, the white dots are very close to the true relationship, okay? So we have low bias in the long run. In the long run, the average of all of these different models is going to get it right, okay? However, if you only had to pick one, you have no idea which one you're going to get, and there's high variance from one line to another, right? So, you know, the ideal solution is to get something in between. So here is like, I don't know, slightly wavy spaghetti, okay? And so here you have some variance, okay, and not a ton of bias, right? So if you look at the average of all of these things, the white dots do align with the true relationship in black quite closely. There is some variance from one random line to another, but it's not as crazy as, say, this one over here. Okay, so this is like something a balance between our two extremes here. All right, so that concludes what I wanted to say about the bias variance trade-off, and so I'm going to keep moving on, and I'm going to now introduce an entirely new topic. So when I teach this class in the regular quarter, like this would have been the end of a week, and then we start another one. But because of the summer schedule, like the schedule's thrown off. Okay, so anyway, I'm going to just start introducing neural networks here. So neural networks, well, let's talk about it. It's basically a design for a function. Okay, it's a way for so linear regression is a design for a function. You just take each of your predictors, you multiply them by a coefficient, and you add them up. That's linear regression, multiple linear regression. Okay, neural networks is the same kind of thing. You have your input variables x, you're going to multiply them by some stuff, but you're going to do additional stuff to it to make a prediction. Okay, but it's the same kind of idea. You just have inputs, you do stuff with your inputs, and you get a prediction. So in that sense, not too complicated, okay? But the way you do stuff in between has gotten quite a bit complicated. So we're going to just start off with a very, very, very simple example of a neural network, okay? The simplest kind, the forward feed neural network. And we'll just have one hidden layer, okay? And these types of neural networks have been around for a long time, like 50 years, things like that, okay? And, the 50-year-old neural network, its performance was okay, but not super great. What we've found, though, is that more recently is that if you just follow the same design, but you just make it a lot bigger, okay? Your hidden layer has a whole bunch of nodes, and then you have a whole bunch of these hidden layers, then like somehow, almost by magic it feels like, the things get really, 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 really good at predicting stuff, okay? And pretty much like all of the AI stuff that we're seeing today, these large language models, these are just neural networks. They're just neural networks, but they're just really, really, really big, okay? They're just really, really, really big with a whole bunch of hidden layers. They do some additional things in between the layers, and they have stuff to kind of keep track of attention, and there's like kind of a whole lot of work that was done in terms of like how do we turn words into numbers, okay? That's like an important thing because neural networks are really just you're just multiplying matrices, okay? You're just multiplying these really big matrices, and I guess a higher dimensional matrix we call a tensor, but you're just basically multiplying these big matrices or arrays or tensors together. And when you multiply that, you need numbers, and so how do you go from words into numbers and then numbers back into words? So that's what's going on. But at the core, it's just a neural network where we're multiplying one matrix to another. We're going to start up by looking at just the simplest neural network here, okay? And what did I say? Okay, so in overly simplistic sense, a neural network is a design for a function, takes input, does computations, produces an output. The inspiration for the neural network is the brain, because I guess somebody said, hey, if you think about the brain, it's really just electrical impulses going from one set of neurons to another set of neurons, and then somehow that, saying this, it's crazy, but somehow just those electric impulses going from one set of neurons to another set of neurons allows us, gives rise to consciousness and thought and reasoning and creativity and all kinds of stuff. Anyway, I'm following an example. I linked to this playlist, okay? We have a playlist from Welch Labs, playlist from Through Blue, Warren Brown. These are old playlists at this point, but they're still good. The content is still good. And so the example used in Welch Labs has two input variables, okay? And that's going to be represented by having two columns in our X matrix, okay? And then we have one set of values in Y, right? And so just for fun, like the Welch Labs author named these things like hours of sleep and hours spent studying, okay? And this is exam score, but it could be anything you want, okay? You could have just basically your first column is one X variable, your second column is another X variable. And what we want to do is we want to predict our Y, okay? And so the way we set up our network is we're going to have an input layer, the values coming in, and then we multiply them by a matrix to go to our hidden layer. We'll multiply them by another matrix to get to our output layer, okay? But you can have a whole bunch of hidden layers if you want, right? So we're going to, so our input layer is going to have two nodes because we've got two columns. We've got one node for each variable, okay? The output layer is going to just have one node, which is just the exam score. And then we'll have one hidden layer in our example with some arbitrary number of nodes. So here I'm picking one layer with 3 nodes, okay? And I'm just picking small numbers to keep our example simple. And again, if you go to another, like the AI ones just have a lot more nodes here, okay? So our input layer, we have 2 nodes in the input layer, 3 nodes in our hidden layer, 1 node in the output layer. I've got arrows. Every node in this layer is connected to every node in the next layer, okay? And so this node is connected to all 3 nodes in the next layer. This node is connected to all 3 nodes in the next layer, okay? And so I've got 6 arrows between the input layer and the hidden layer, okay? Each node here is connected to every node in this one, and I only have 1 node over here, so I have basically 3 times 1. I've got a total of 3 arrows here. But each of these arrows represent a weight, okay? And we're going to gather our weights together in a weight matrix, and basically what we do is we take our input values, multiply it by the weight matrix to get these values, and then we're going to take these values, multiply it by the next weight matrix, which gathers these 3 values together to kind of get our value in our output layer. We also apply functions like we apply some activation function at each layer, but this is the structure. Input values, multiply it by some matrix here to get kind of our next thing, multiply by a matrix to get kind of our next thing here, okay? So deep learning, all of the AI stuff, all of our image recognition, this is all powered basically by a neural network. It's just rather than having 3 nodes in your hidden layer, you have maybe 1,000 nodes, okay? And rather than having 1 hidden layer, you might have 100, okay, or 1,000 hidden layers or something like that. And so you end up having, billions and billions of arrows or these weights connecting all of these layers together, all right? So you have a whole bunch of parameters, and now our neural networks are really, really, really good at performing tasks that we didn't think computers could do for a long time. So, we kind of take it as granted now, but the idea of computer vision, like if you were in the field of computer science, like the idea of computer vision was, almost like a fantasy a long time ago. You go back a couple decades. But now it's like you can take a picture and you can say, hey, what is in my picture? And it'll say, oh, that's a picture of a chair. That's a picture of a dog, and things like that. And this was actually a very difficult problem. And a lot of research was done with this thing called ImageNet, where you had all like millions of images and thousands of possible labels, and say, hey, this is a dog, this is a cat, this is a chair, a bicycle, a horse, all kinds of things. And humans probably are like 95% accurate. And then in 2015, so I guess that's already a decade ago, okay, the computer beat the human, okay, and now they consistently beat the humans. And you're like, well, how hard can it be to label images? It's hard because you'll have like their tiny little postage stamp images, not very high resolution in this image set, and you'll have things like, oh, this is not just dog, but it'll be like dog, you know, I don't know, golden retriever, dog, Labrador, dog. You know, have a bunch of different breeds of dogs and things like that and stuff. So anyway, neat stuff you can do with neural networks. All of the cool AI stuff is powered by neural networks. Neural networks are really, really good at prediction, and that's why they're so popular, because again, that's kind of like the only thing we care about now. But if you want to explain and interpret the neural network, it can't be done. Okay, what happens inside? We can just say, oh yeah, this is how we designed the neural network, and we made some of these tweaks to kind of improve its performance, and we're doing this to the model, so we can do that. But we adjusted our reward function and things like that. But then once it's been, quote, trained on the data, so like once you have your data and you say, all right, neural network, learn this data, and then we ask later, hey, what is this node doing? What is this thing? Like, nobody can explain anything, right? So when we talk about like, oh, the algorithm, whether, on YouTube, you have the algorithm and it's recommending videos to you, and you like it, right? Like, you like the videos that your YouTube account recommends to you because it has learned your preferences. And so like if you borrow someone else's phone and you look on their YouTube, you're like, what are all these videos that you're getting, right? Because it's not your interest, right? Same thing with like music, and you want to be signed into your account so that you get the music you like and things like that, or whatever social media thing you have. But then if someone's like, hey, why are we getting, I don't know, these crazy videos that we don't really want to be promoting and stuff, can't you just fix the algorithm? And the answer is like, no, we don't really know what's happening on the inside, okay? All we can do is now we can start adjusting, I guess, reward functions and start punishing things. But, right now the way the quote algorithms, the way the neural networks are set up, it's just saying like, oh yeah, well, I'm optimizing, I'm trying to maximize, our rewards and things like that. So anyway, okay. But anyway, back to our network. This is what we have. 2 nodes at the input layer, 3 nodes at the hidden layer. We've got 6 arrows or 6 weights that connect our input layer to our hidden layer. We got 3 nodes at the hidden layer, 1 node at the output layer. We have 3 weights going from our hidden layer to our output layer, okay? So our 6 connections and our 3 connections, we gather them together into a matrix, okay? And we're going to label each of these terms, okay? So we have this first weight. You see 3 numbers here, okay? The superscript in parentheses is which, I guess, weight matrix it belongs to. So it's superscript 1 to say it belongs to our first weight matrix. Okay, over here, these all have superscripts 2 to say they belong to the second weight matrix, but these all have superscript 1 to say they belong to the first weight matrix. Okay, and then you have 2 subscripts down here, 1, 1. This says it's going from node 1 to node 1. Okay, this arrow, okay, the blue arrow going from node 2 in the hidden input layer to node 1 in the hidden layer is W subscript 2, 1, okay, going from node 2 to node 1, okay? This purple line, this purple arrow going from the first node to the second node is W1, 2, and then the red line going from the first node to the third node is W1, 3, all right? So that's how the each of these weights are labeled. Okay, so each weight has basically which matrix it belongs to, which node it's coming from, which node it's going to. Okay, so this one is W super 2 sub 1, 1. This is W sub 2, 1, W sub 3, 1. Okay. And so, so we'll gather them together in our weight matrix, okay? So this first row is basically all of the arrows coming from the first node, okay? So we have W11, W12, W13, and then the second row is all of the arrows starting at the second node, okay? And then the columns are basically which node they are going to, okay? So this first column are the arrows going to the first node. These are the ones arrows going to the second node, arrows going to the third node, okay? I tried to color coordinate these. This was a pain to do in LaTeX, so please appreciate the hard work here. But basically, so these are the blue arrows go to the first node here, right? The purple arrows go to the second node, the red arrows go to the third node, right? So this is how we arrange our values, and you can take this and generalize to a much bigger matrix with more nodes and whatnot, but this is what we have, okay? All right, and so when to go from our inputs to our output, we follow a process called forward propagation, okay? Forward propagation basically takes your input values in X, and the goal is to get to our output of Y. So what we're going to first do is we're going to multiply our input values X times our first weight matrix, W superscript in 1, okay? So our X observations, we have two variables and we have N observations, so N rows. So we're going to have N by 2 multiplied by our first weight matrix, which is a 2 by 3. And so the result is going to be an N by 3 matrix. We're just going to call this Z2. But basically, we take this, and so you can see everything in this first column is everything going to that first node. Everything in the second column is basically all of the values in the second node, and these are all the values in the third node, okay? And the observations, basically our first observation is just the first row, and then the second observation is in the second row, okay? And then after we apply forward propagation, we will apply a function to every value in this Z matrix, okay? And we call this the activation function. Okay, so you just have some kind of arbitrary function that you're going to apply to every single value in this matrix, okay? And so this doesn't change the shape of the matrix, okay? Because we're just applying the function to each value individually, okay? So this is just a univariate function. It's just taking this one value, applying a function, and you're getting one value back, okay? This is the activation function. Now, as far as activation functions go, it can be anything, right? It could just be the identity, and you don't actually do any kind of transformation. But it can be, like historically, a popular activation function was the sigmoid activation function. Basically, looks like it's the logistic function. Have a plot of this, yeah. So this is the sigmoid activation function, and basically it takes values going from negative infinity to positive infinity, and it squishes them from 0 to 1. So if you have t to be a very large positive value, basically e to the negative t becomes 0, and you get 1 over 1, and you get it's equal to 1. If t is a very negative value, at a very negative value, it's 1 over infinity, and that becomes 0, okay? And then when t is equal to 0, you have 1 over 1 plus 1, or 1 over 2, and you're at 0.5, okay? So this is the sigmoid activation function. This is the logistic function. So this was a popular function historically in the development of neural networks, and that's what we'll use initially. Today, we don't really use the sigmoid activation function anymore. Okay, so this is not, it has fallen out of favor. It is no longer really used. And we use things like the ReLU, okay, rectified linear unit. That's probably the most popular activation function these days. There's, other ones like hyperbolic tangent, and the leaky ReLU and all kinds of stuff, and you can read about them on Wikipedia. But we'll go ahead and stick with the sigmoid function just because as far as our analysis goes, we can calculate the derivative. The ReLU, the derivative doesn't exist at certain locations, so our process does become a little bit harder in that way. But computationally, ReLU is simple. Computationally, the sigmoid, like from a numeric computer workhorse thing, this actually is a little bit tougher. But as far as the calculus goes, I would say the sigmoid function is a little bit easier for us. Okay, so anyway, this is what we have. And so so what we've done is we've taken our input matrix X multiplied by our first weight matrix W. We get our value Z. Okay, then we apply that activation function to all of the values Z here, and we have our activated values that we're going to call A right here, which is n by 3. And then we're going to multiply that by our next weight matrix, which is W. So if we have our activated values here, and I multiply it by W, then the result is going to just be one column of values. Okay, so our A matrix has three columns of values, but I'm going to multiply it by 3 W, which is 3 by 1, and so now I'm going to just get one column of values. Okay, and so you can see we're adding up, all of these things. So we just have one column of values, which is going to be my values Z. And then with our values here, we will apply an activation function again. It can be the same activation function. It can be a different activation function. At every layer, you can have different activation functions. Here, we're going to go ahead and just apply the same exact activation function that we used earlier. Okay. So our forward propagation looks like this. We're going to take our X matrix, multiply it by our first weight matrix to get Z2. Then we're going to apply our function F to every value inside Z, and we get our activated values, A2. We're going to take A2, multiply it by W2, our second weight matrix, to get Z3. We're going to apply some kind of activation function here. Here I'm using the same activation function, but it could be a different one, to get my y-hats, my predicted values. And that's what we have, okay? We can also include bias terms, okay? Bias terms are basically like intercept values, if you want to include just like a constant. And this has the effect of just kind of sliding the activation function left or right. And you would have a bias term for each node. So when you have this, you would have the same one bias value that just gets added to every single value coming into the second node. And here you have, so the superscript here is like kind of our first set of biased values. And we have subscript 1 for our first node, subscript 2 for our second node, subscript 3 for our third node. And so for here, the operation we do is we multiply X times W, and then I basically want to add a bias value to all of these things. However, the matrix containing my bias values is a 3 by 1, okay? I mean, I guess I could have specified it as 1 by 3, but right now I have it 3 by 1, and I need to combine it with this matrix of basically Z values here, or basically X times W values, which is in the shape of n by 3. Okay, I've got n rows, 1 for each observation, 3 columns. So I can transpose B so that I have 3 columns now, but then I'm going to multiply it by a column of 1s, which we'll call J. Okay, and this I have n observations, so my J is going to be length n. This is just an arbitrary thing to indicate that I want basically the same row applied to all of these things. Okay, so basically this is going to be my column of J, column of 1s that I call J, and this is my basically row of bias values. And so the result of this is going to be an n by 3 matrix where the first column is all just B1, the second column is all B2, and the third column is all B3. Okay, and then I'm going to take this matrix, which is x1 times w1, or x times w1, which is going to be n by 3, and then I'm going to add it to this, the resulting matrix over here, which is also n by 3, and now the result is going to be n rows and 3 columns. Okay, so B1 gets added to every single value here, B2 gets added to every single value down this column, and B3 gets added to every single value down this column. I think I got my subscripts correct here. Okay, so that's what we have here. And we do something very similar for our second matrix of biases. So here, because I only have one node here, I just have, here it's just a single scalar value. So it is, in this case, it's silly to transpose a single scalar value, but in a different matrix or different neural network, you might have multiple things, and your bias terms might be gathered in a column vector. And so here I'm going to transpose that and add it here. And so here I just have one value. I'm going to just add the same bias value to all the values down the column there. And, that's what we have there. Okay, so that's our bias values after taking our activated values and multiplying by your second weight matrix. And so if you gather them all together, then this is what we have, right? So with bias terms, we have x times w plus j times b1 and so on and so forth, okay? I do want to kind of just pause here for a moment and just say what we're doing is not linear algebra. Okay, we're dealing with matrices, we're dealing with vectors, and we like to use the notation of linear algebra. It's a convenient notation to talk about multiplying vectors and matrices together. Okay, however, we are going to be doing things that is not allowed in traditional linear algebra. Okay, so we will do things like element-wise matrix multiplication. Okay, so if you have like an n by 2 matrix over here and another n by 2 matrix over here, we're going to do element-wise multiplication where you take the element in the corner and this corner and multiply them together, and the element in this the second elements, multiply them together, and so on and so forth. So you're going to do like an n by 2 matrix, element multiplied by another n by 2 matrix to result in another n by 2 matrix, okay? Which in traditional linear algebra, you don't do stuff like that, okay? So, you can do an n by 2 times a 2 by n, or a 2 by n times a n by 2, or things like that, but not element-wise multiplication. So, we're going to introduce additional symbols and things like that to kind of handle these non-traditional linear algebra operations, okay? At the end, what we're really doing is we're multiplying just a bunch of numbers and adding them together, okay? So, you have values coming in your X matrix, okay? They get multiplied by weights, you add constants, we're doing stuff, and we follow some process to get some output value. And so if you need to, you can always kind of just follow one element and follow it along, and it's really just being multiplied by scalars and constants and things like that. Okay, we're going to wrap things up a little bit early. Where we're going to next, okay, is we're going to measure loss. So we have a way now to do forward feed, which goes from our inputs to our predicted values y hat. Okay, so we go from our x, we have our current weights and our biases and all of that. We get some predicted values y hat. What we're going to do next is we're going to measure our performance. We're going to take the difference between our actual values and our predicted values, and we'll square those up and add those up to get kind of the measure of our performance. So ideally we want the difference between y and our y hats, our actual and predicted values, to be as small as possible. So we want our loss to be minimized. And the way we're going to minimize our loss, the only thing we have control over are the values in our weight matrices and our bias terms, okay? We don't have control over the actual y values. We don't have control over the x, right? These are fixed values because they are part of our data, okay? So the x is fixed, the y is fixed. We can change our w's and our w1s or w2s, and when we do that, that will change our predicted values. And so we're going to try to tweak whatever w1s and w2s are to get our resulting y hats as close to y as possible. And so, so we'll do that next week. We'll take a look at that next week, and that's going to be done via gradient descent, okay, which we introduced earlier. So, so we do gradient descent to try to figure out what's the best W's and B's to use, and that will hopefully improve our y hats, and then we'll improve all of this. Okay, so that's what we'll see next week, and so we'll just wrap things up here, end a little bit early today, and we'll see you then. Have a great weekend.